Good evening, everyone. I'm Professor Andrei Zvelindovsky, Head of School of Mathematics and Physics, here in University of Lincoln, in United Kingdom. Thank you for everyone who came in this sunny evening here in Lincoln. So I'm almost blinded by sun setting. Just before we start, so to ensure that everyone can hear as well, if you hear as well, maybe you put thumbs up in a live chat, or just some yes, we can hear you well, just to ensure that everything runs smoothly. Because there was a little bit of echo. Yeah, is the echo disappeared? Yeah, is the echo disappeared? Yeah, is the echo disappeared? No. 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 There is still some echo, it looks like. There is still some echo, it looks like. There is still some echo. Problem with echo. Problem with echo. Problem with echo. Your echo is still there, right? So your echo is still there, right? So your echo is still there, right? So and just give us please a couple of seconds. We're trying to see what happens with this echo. What happens with this echo? What happens with this? Can anybody hear me?
Yes, and there's no echo.
Can anybody hear me?
Oh, echo's back.
Yes, and there's no echo. Did you hear me?
Yes.
Don, if you try to say something. Don, if you try to say, if you.
But you've got echo. Let me go on with my talk and let's see if I've got the echo.
Let me go on.
Sergey, put me live and let's see what happens.
Sergey, put me live and let's see what happens.
Oh, is the echo gone?
Oh, is the echo gone?
Everything seems repeated. Everything seems repeated. Restart whole session.
Good idea.
Restart whole. Hello, if there is anybody still there who can. Say if there is any echo.
I'm not hearing any echo now. Good. No echo.
Okay, so it looks like there is no echo. Right, so we're not quite sure how we managed to sort this echo problem. But we're going to continue with yes, so there is no echo, people, right? So right, okay, so thank you very much for staying with us. Thank you for returning to listen. We do apologize for this technical issue. It is quite challenging to connect across the space, and I'm kind of sweating here in Lincoln. And Don told me that he is a bit freezing in the middle of winter. Is it right, Don?
Yes, it is. It's absolutely freezing here. It was only 19 today.
Yes, so that is middle of winter in South Africa. As we lost quite some time, so we will not have a lengthy introduction of Don. Everyone who doesn't know who is Don Kurtz is, please click on the link in the descriptors of this video, when you can read the biography of Don in full detail. Now I'll give floor to Don to his talk, which hopefully will be without any echo.
Okay, thank you, Andrei, and good evening, everyone, or for those of you who are still with us. I don't blame those who drifted away not knowing what was going to happen. Let me just bring up the talk and let's get started, giving our timing. So here comes the PowerPoint. And I need to know from somebody, Andrei, are you seeing that? Andrei? Right, I'm going to presume that you all are seeing this. And we'll start talking about the sun today, hot with storms. That picture in the background is a beautiful ultraviolet movie of the sun. Let me start that for you. And we will come back to that and I will explain it in more detail, but that's perhaps the sun as many of you have not seen it before. This is a beautiful picture of the Earth from quite an unusual perspective. This is from an Earth observation satellite that is actually orbiting in a polar orbit. And the picture's been put together from many individual pictures. But there's an unusual look at our planet, looking down almost over the North Pole. You'll see, let me bring my laser pointer up here, just a moment, laser pointer. You'll see the UK over here. Most of you are in the UK. There it is. And Greenland is quite visible, and then the Arctic ice cap right here. And of course, our beautiful blue planet is powered by the light from the sun. But we get more than the light from the sun. The sun puts out lots of particles. It has a wind, it has flares and mass ejections, and those impact on the Earth and produce some incredible effects here. And that's largely what I'm going to be telling you about this evening. Now, here's a picture of the sun that I took a few years ago in early July at midnight off the North Cape of Norway. There's a picture of the midnight sun. And a friend of mine in Norway, another astronomer, Jan Erik, tells me that he had a woman visiting from Los Angeles who had come to see the midnight sun. And after she had seen it, she came to him quite irate and said that when she got back to Los Angeles, she was going to sue her travel agent because she came to see the midnight sun and all she got to see was the regular old sun. Now, we don't know what it is that she thought she was going to see, but I have to tell you that that's the sun as you see it. That's the regular old sun, but tonight we're going to see the sun, and it's not very regular at all. Here's today's picture of the surface of the sun, taken from a satellite mission called SOHO, the Solar and Heliospheric Observatory. It's been in orbit since 1995, incredibly successful. It's funded at least through 2025. And this was the picture of the sun early this morning at 7:30 GMT, and you'll see quite a few spots on the sun. Now, I'd like to remind you or tell you that the sun's diameter is 110 times the diameter of the Earth. And so many of these spots here are actually bigger than planet Earth. And we'll get an explanation of those spots in just a little while. Here's a movie taken by a satellite orbiting the sun called the Solar Dynamics Observatory, SDO. If you look at the bottom, you'll see that the movie is sped up to where 1 hour is approximately equal to 1 second. Now, the sun takes 26 days to rotate at its equator, and so you're seeing that it's nearly monthly rotation right there. And you're also seeing the pyrotechnics. You're seeing the magnetic loops, the flares, the reconnections of magnetic fields. You're seeing the glow of exceedingly hot gas out beyond the atmosphere that you can see in the regular old sun when you take a glance at it with your eye. And here's an artist's impression of what the inside of the sun is like. And let me describe that to you some so that we can understand what's happening on the surface of the sun. Deep in the core of the sun, the temperature is 15 million degrees. And at that temperature, the lightest gas, hydrogen, is being fused to the next lightest gas, helium. And that's what produces the power to make the sun shine. That energy that's produced works its way out of the sun. Here it says as a random walk. And it takes nearly 1 million years once the energy is created for it to leak out of the surface of the sun, because the photons, the particles of light, are constantly being absorbed, re-emitted, scattered in random directions. And it takes 1 million years for them to leak out. When they get about 70% of the way out here, the gas can no longer transmit the energy just by transmitting the light. And that makes the gas actually start to boil. We call that convection. And this outer 30% of the sun is just seething with convection, hot rising columns of gas and cool falling columns of gas. And over here on the surface, you'll see that it's just dotted with these little yellow dots everywhere. Those are called granulations. And they're the tops of these convective cells where hot gas is rising. Hot gas is brighter than cool gas. These dark lanes you see is where that gas then returns cooler and falls back down into the sun. And just to put it in perspective, each of these little yellow dots are about the size of the United Kingdom. Now, they're about 1,000 kilometers across. Out in the very outer part, the gas outside the surface as we see it is heated by mechanical heating to where it rises to 500,000 to 2 million degrees in the corona, the most outer part. The lower part, where it's 50,000 degrees or so, magnetic fields reach out of the sun and capture the gas, and as it cools, it glows, and you see these loop prominences, some of them quite gigantic. And we occasionally get those things snapping, reconnecting, and they put out coronal mass ejections, eruptive prominences, and flares that blast out into space. And when those things hit the Earth, we are impacted significantly. We are occasionally impacted quite dangerously, and I will come to that by the end of this talk. Here's a movie from NASA, taken with the SDO, where an amazing flare went off on the limb of the sun. It just happened to catch this flare right on the limb where it can be seen best. There it is over here. Now this movie is sped up. 1 second in this movie equals 6 minutes. It's sped up 360 times. And I think if the woman from Los Angeles could have seen this, she would not have considered it the regular old sun. That gas in the magnetic field is cooling, and as it cools, it's denser than the surrounding gas, and so it falls back onto the surface. Oops. There's a picture of the Earth put in here. Graphically, just to give you the scale, this arch is much, much bigger than the Earth. Notice the rest of the sun seething over here with all of the gases rising and falling, and jets shooting out. And so here's a very quick movie. It's actually an hour, but sped up to just a matter of seconds, of an eruptive prominence coming off the sun with billions of tons of gas, primarily hydrogen, blasting off the surface at speeds up to 2,000 kilometers per second. And sometimes those are aimed at the Earth. Now this is now a white light picture of the surface of the sun. And again, it's sped up, but we're going to watch the rotation of the sun. And here's a gigantic sunspot over here. And these flares and mass ejections are often associated with these sunspot regions where strong magnetic fields are reaching out of the sun. But these are constantly changing. And let's run this movie and watch how they vary with time. Now remember, the sun takes 26 days to rotate. And so as we watch this movie, days are going by. But you can see the character of that gigantic sunspot group changing. So the sunspots are highly variable. Here's a beautiful picture looking down deep into a sunspot. This is going to be a movie in a moment, but before I run it, let me explain a few things. These are the granules, these bright yellow spots that you see, those are the tops of the hot rising columns of gas. And as I said, each one of these is about the size of the United Kingdom. The center of this spot is not actually dark. The gas in the center is about 4,500 degrees. And at that temperature, it shines very, very brightly. But the surrounding gas is 6,000 degrees and it's much brighter. And so when the picture is exposed so that we can see this outer part without it being overexposed, the middle part, which is fainter, looks dark in comparison. Now, the pictures are being taken at a regular rate. And because of that, when you watch this movie, it will appear as if the gas is flowing into the sunspot. It's actually flowing out. And this is what's called a stroboscopic effect. It's the same effect you get in, say, a cowboy movie. You've almost certainly seen this when a wagon's coming into town, and as it slows down, it looks like the wheels stop and then go backwards for a while. That's a beating effect between the rate at which the camera's taking pictures and the rate at which things are happening, in this case on the sun, in that case in the movie. And so as we watch, this gas is actually flowing out of the sunspot. But look at how the granules are changing on the side. The surface of the sun is just incredibly dynamic. And here's how the pattern goes over centuries. Sunspots have been seen for thousands of years. Occasionally they're so big you can see them with your naked eye. Now, don't look at the sun with your naked eye. You already know that because you've done it a few times in your life, and it's blindingly bright. And if you look for very long, you can do eye damage. But occasionally, even before there were telescopes, get a situation where the sun would be rising early morning and there was thick fog and the sun was dim enough that you could glance at it with your eye. And I've seen that for myself. Occasionally, there are sunspots so big you can see them with your naked eye. And so humans have known about sunspots for thousands of years, but not understood what they were. Telescope was invented in 1609, and Galileo immediately saw some sunspots. And then for a period of nearly a century, the sunspots disappeared in what was called the Maunder minimum. And this particular diagram, called the butterfly diagram, shows them since the 1870s. So on this top plot, it's time along the axis in decades. And the other axis, the vertical axis, shows the latitude on the sun from the equator to the North Pole and to the South Pole. And what this shows is that the sunspots start appearing on the sun at the beginning of its 11-year cycle at latitudes of about 30 degrees north and 30 degrees south. As you saw in that previous little movie, the sunspots are not stable. They usually last for a couple of weeks to maybe a month and a half. And as the sun rotates, as time goes by, those sunspots disappear and new sunspots appear. And with time, the sunspots appear closer and closer to the equator. Now, if you look at the bottom plot, it's showing how many sunspots there are. And so there's a peak in each cycle, and you can see that these cycles are very different. There was a gigantic sunspot cycle back in 1957, which had major impact on the Earth, and also on what was called the International Geophysical Year, when the sun was studied in great detail at the time of this incredibly large maximum in the solar cycle. As the sunspots drift down to the equator, they get closer and closer to the equator. The number goes up at first and then down again, as you can see in the bottom. And then just as they get near the equator, they start to disappear and new ones appear back up at 30 degrees north and south. Now, the sunspots are like little magnets. They come in north and south poles. And during one cycle, the polarity in one hemisphere is north and south, the other hemisphere it's south and north, and during the next cycle those are reversed. So really the cycle's about 22 years long with the magnetic reversal. This is called a butterfly diagram because it kind of looks like a group of butterflies across here, and there you can see that pattern of sunspots over the last century and a half. That sunspot cycle is only partially understood. We have observations now to show that other stars have similar cycles, and the times on the other stars can be as short as just a couple of years to a couple of decades. And so the 11 years is particular to our sun. Here's another look at that solar cycle in just the numbers. And we have numbered these solar cycles starting back in the late 1700s in what's called a Carrington number. And I'll come back to Carrington in just a little while. And so those are the numbers of each of the cycles. And we're now going into cycle 2025, then cycle 25 now. And the prediction is that it will peak around 2026. And there you can see the prediction. The height of that cycle has a great impact on radio communication, on aurora, and other things I'll talk to you about as we get to the end of this. Now, there's a picture of a magnet with some iron filings. I hope that this is something you've done for yourself at some time during your life. I certainly did when I was a child. Go out to a sandbox with a little magnet and just run the magnet through the sand and pick up iron filings, and then put them on the top of a piece of paper, put the magnet underneath, and look at how the filings align with the magnetic field lines. The magnetic field lines describe the magnetic force, and you can see the magnetic field reaching from North Pole to South Pole. And the sun has a dipole magnetic field, and it does the same thing. So here's a cutaway looking into the sun. It rotates in 26 days at the equator, but 35 days up at the poles. Now, the sun's entirely made of gas. There's no solid. It's entirely gaseous, primarily hydrogen and helium with a little bit of other stuff. Equator going around faster than the poles. And it does have a dipole magnetic field going from the North Pole to the South Pole, as does the Earth. And so these are the magnetic field lines. But the sun is made out of hot hydrogen gas, and much of that gas is ionized. The protons and electrons have been pulled apart. They're charged particles. Charged particles experience a force when they try to cross magnetic field lines. So slow-moving charged particles get trapped in the magnetic field lines. The fast-moving ones that have energy have got so much energy that they drag the magnetic field line with them with the rotation of the sun. And as you see in these next two diagrams, that actually drags the magnetic field in the sun out, and it wraps it up around the sun until it's in a bunch of loops, almost like ropes of magnetic field. And then those hot rising columns of gas that make those granulations can drag those ropes of magnetic field and make them pop out through the surface. And so here comes a North Pole down to the South Pole of the field, and the sunspots will form at the base of these magnetic loops. Gas will get trapped in the magnetic loops, and you can see that directly when you look at the sun in very short wavelength light, particularly ultraviolet light, which sees much higher energies and gives us a view above the surface of the sun. Now, we can't see that ultraviolet from the ground. It doesn't penetrate the atmosphere, but these satellites that we have out in space orbiting the sun, the SOHO satellite, the Solar Dynamics Observatory, now the Parker probe, which is very close to the surface of the sun, can look in the ultraviolet, and we can actually see these amazing loops imaged. This is a picture from this past April, just a couple of months ago, of a total eclipse of the sun. Total eclipse of the sun is one of the most amazing things you can see in your life. It's absolutely unearthly, to say the least. Those of you who have seen one or more know that you're hooked on them when you see them. They only last a few minutes, and you'll then chase them. This picture was taken at Exmouth, and those of you who are in England, many of you are, may wonder why you didn't go down to Exmouth to see this particular eclipse. And the reason is that it was in Exmouth, Western Australia, not the original Exmouth in the south of England. There in this picture, using digital photography and many exposures at different lengths to give us contrast, you can see the incredible way the magnetic field of the sun guides the outer corona where the temperature of the gas is 2 million degrees. You can see, if you look closely, the prominences down on the surface. And if you look really closely, you can actually see the surface of the moon, which is being lit up by the full Earth, because the moon, passing right in front of the sun, is new. The Earth is out in the opposite direction, and it's incredibly bright in the sky and lights up this side of the moon. Now, with your naked eye at an eclipse, during totality, you don't need any eye protection. It's safe to just look with your eye, and you can actually see more detail than you can see in this amazing picture if you go to an eclipse live. The SOHO telescope takes images regularly of the sun, many different wavelengths. This is extreme ultraviolet. These are measured in angstroms of light. We can see in the visible from about 4,000 to 7,500 angstroms. This is way out in the ultraviolet at 171 and 195, 284, giving us looks at different depths in that outer part of the sun. And then there's the visible image right there. And it's that I just downloaded this morning and showed you a little while ago with the sunspots for this morning. And then there is a large angle spectrometric coronagraph on the sun, which blocks out the sun so that we can see what's happening dynamically. And let me show you a LASCO movie of the surface of the sun. Now that's going to repeat. Let me stop it and explain it to you. Oh, if I can get it to stop. Right, I'll explain it to you while it goes. This dark circle is blocking out the surface of the sun. The sun would be the size of this inner white circle that's been drawn on the picture. This dark line that you see right here is an arm that's holding this coronagraph in front of the sun. The sun is moving to the left through the stars, but we're staying fixed on the sun, so that makes the stars look like they're moving to the right. And of course, that's a comet coming in that's being evaporated by the sun. The LASCO instrument on SOHO has discovered over 4,000 comets. Some of them crash right into the sun. But what I want you to watch is the sun has a constant wind blowing out off of it at all times, typically 500 kilometers per second. And then it has coronal mass ejections. There went one right there. There's another one. Big blasts out into space. They go out 2,000 kilometers per second, carrying out billions of tons of material. And those were going off to the side. If they're aimed at the Earth, we get clobbered about 2 days later, and I'll show you what happens. Here's a diagrammatic look at it. Here's the wind coming from the sun, and it encounters the magnetic field of the Earth, which is also dipolar. Here are the magnetic field lines of the Earth. But that wind from the sun gets both captured in the Earth's magnetic field, and it also drags the magnetic field out in what's called the magnetotail. And so in the direction opposite the sun, the Earth's magnetic field gets stretched out far into space. Here in close to the Earth are two belts called the Van Allen radiation belts. The outer one is material captured from the sun, very high energy. The inner one is much lower energy particles that are largely captured by cosmic rays coming from far out in intergalactic space and colliding with the Earth's atmosphere. Now, these particles coming from the sun are primarily hydrogen, so that means protons and electrons. And as the electrons get captured in this magnetic field, oh, there's a picture of James Van Allen, after whom the Van Allen radiation belts are named. He was very famous for that, working in University of Iowa back in the 1950s after that 1957 solar maximum. And here are these particles spiraling around the Earth's magnetic field lines. As they come down towards the pole, the magnetic field lines squeeze, and that acts as a mirror, and the particles bounce and they go back again and come down to the South Pole, where they bounce and come back again. So they're bouncing back and forth about twice per second. They're going a large fraction of the speed of light, from south to north to south to north, at about the rate that I'm saying that. And where they come down and collide with the Earth's atmosphere, near the North Pole and the South Pole, at the magnetic poles, they produce the aurora. They make the air glow. Here is last night's auroral prediction from the Space Weather Prediction Center. I'll give you a connection to that just at the end of the talk. And you'll see that the aurora is an oval. The particles in the Van Allen radiation belts are coming down in the magnetic field, and this is where they collide with the Earth's atmosphere. And this green right here indicates that if you had been up in the north of Scandinavia last night, there would have been a good chance that you would have seen some aurora. If it were colored red, it would be absolutely guaranteed. If it weren't for the fact that you can't see the aurora this time of the year in the northern hemisphere because it's daylight all the time. Remember the midnight sun. There's the shadow. The sun does not set in this part of the world, so no aurora at this time. If you ever would like to go hunting the northern lights, say in Scandinavia, of course, that's something that you'll do somewhere from the equinox through the winter, preferably in the winter where it's dark almost all the time, and you can see the aurora when it happens. Here from yesterday is the auroral oval over Antarctica, and they would have been having some pretty decent aurorae down there, but of course there's nobody there to see it, almost nobody on the continent, and virtually no one out at sea between Antarctica and Australia here. Beautiful pictures of the aurora. To see it with the naked eye, if you really get a great auroral storm, you may see it like this, but the camera actually accentuates it, and these pictures often look even more beautiful than what you see. But in an extreme storm, you really do get to see shapes like this, and they are just constantly changing. It's totally dynamic and changing in a matter of seconds, always changing. Here's a movie from the European Space Agency. This is taken from the space station, and the space station, even above the Earth, the astronauts can see the aurora. Now, this is very much sped up, but they're actually up above it mostly. It reaches high into the Earth's atmosphere. And a story to go with that, I worked in Japan repeatedly over the last 40 years, and on one of my flights from Paris to Tokyo, we were flying over Siberia. It was back before Russia went crazy and started this current war, and the flights would go over northern Russia, and I intentionally chose a seat on the northern side of the plane at the window. And during that night, we were flying through a geomagnetic auroral storm, and the sky was just, for 6 hours, constant activity of aurorae. I sat there glued to the window and watched it the whole night. I did look away occasionally. I looked around the cabin, and I was the only one watching. Everyone else was either watching a movie or sleeping. Nobody else in that entire plane watched that incredible auroral event. I actually don't quite understand why the captain didn't announce it, but I guess he thought people would prefer to sleep. And so just a little diagram. As those high-energy particles, electrons, come down into the Earth's atmosphere, they smash into the molecules in the Earth's atmosphere. The Earth's atmosphere is mostly made of nitrogen and oxygen. And down here, a couple hundred kilometers above the ground, where those particles ram into the nitrogen, that can produce the red aurorae, which are less common but are seen. Higher in the atmosphere, the electrons hit oxygen, and that oxygen then, with the electrons excited in the oxygen, glows with that typical green light that you can see in the aurorae. In 1989, there was an incredible flare that went off on the sun. There was a naked eye sunspot. Now, I happened to be at a little game park up on the Mozambique border at that time. It's called Ndumu, and got up to a very foggy morning where I could see the sun rise through the fog, and I actually saw that sunspot. It was about 1/10 the diameter of the sun, which means 10 times the diameter of the Earth. And an X-class flare came off of that. It was aimed towards the Earth, and it clobbered the Earth, and all of those charged particles moving in the Earth's magnetic field are actually electrical currents. And those electrical currents, through the magnetic fields they generate, can generate electrical currents in any conductor on the Earth. And of course, the big conductors on the Earth are our high power lines. And so the extra current generated in the high power lines in Quebec, in Canada, completely blew their power system off entirely. It knocked the entire province out. Quebec's about the size of Western Europe. It's an incredibly big province. The aurorae were seen all the way down to low latitudes. We even saw them from Sutherland in South Africa, which is at a latitude of about 32 degrees south. In a northern hemisphere context, about the same as Los Angeles in America. The aurorae really came down, heading towards the equator with that incredible flare that came off of that sunspot. People in Quebec were very angry that their power had been knocked out, but the power system there, they're called Hydro-Quebec because so much of their power is from hydropower, put out an announcement that all those motorists sitting at traffic lights cursing should realize it's not Hydro-Quebec's fault. The sun did it, not us. Well, way back in 1859, this Carrington, after whom we name these we count these solar cycles, saw the first flare that was actually observed by a human on the sun. This at the bottom is his diagram, and let me just read you this report given to the Royal Astronomical Society. He says, while engaged in the forenoon of Thursday, September the 1st, in taking my customary observations of the forms and positions of solar spots, an appearance was witnessed which I believe to be exceedingly rare. The image of the sun's disk was, as usual with me, projected onto a plate of glass coated with distemper of a pale straw color, and at a distance and under power at which I presented a picture of about 11 inches in diameter. I had secured diagrams of all the groups and detached spots and was engaged at the time in counting from a chronometer and recording the contacts of the spots with the crosswire, so he was watching the sun rotate. When within the area of the Great North Group, the size of which had previously excited general remark, two patches of intensely bright and white light broke out in the positions indicated in the diagram by the letters A and B. And these are these little banana-shaped white bits of light here. That was a flare coming off the sun. We now call it the Carrington event. It's the biggest flare for 500 years, and it clobbered the Earth. Telegraphs were what we had in terms of long-distance communication then, and it knocked telegraphs out. In some cases, it allowed telegraph operators to operate their telegraphs without any battery power because the wires were carrying current without the batteries. The aurora was seen right down to the tropics. And we estimate that that particular flare, the biggest class of flares we call X class, put out a power of 10 to the 27 joules. Now, I want to put that into perspective. How much is 10 to the 27 joules? That's 10 followed by 27 zeros. Well, here's a plot of energy consumption of humans now, going back to 1800, coming forward to 2021. And up here at the top, this top line is 160,000 terawatt hours. Now at home, if you're looking at your energy consumption at home, you're probably measuring it in kilowatt hours. That's thousands of watts times hours. A watt is a joule per second. A terawatt is trillions of watts times an hour. And so I've done the calculation, and this is over a year. This is indicating that we are currently using 10 to the 21 joules per year of energy, generating it by some renewables, primarily by oil and coal, still not renewable. And as you know, we're doing damage to the atmosphere and we're changing the climate. 10 to the 21 joules. Let me just backtrack a page. 10 to the 27 joules is 1 million times greater than that. That flare that Carrington saw, which lasted a matter of 30 minutes, an hour, put out as much energy as we humans are currently generating on this planet if we continued for 1 million years at our current rate. The sun, and for the sun, that's just weather. Now, that was an exceptionally big flare, but it will happen again. What happens when it happens again? If we have a Carrington event today, or when we do, we had one close to that in 2012, and we dodged the bullet. It wasn't aimed at the Earth, but it will disrupt all air traffic control communication with aircraft. We got a problem, especially in places where the skies are crowded, with how we're going to control aircraft. The atmosphere will lift. Low-flying satellites will experience extra drag. They may actually be dragged down and end up burning up in the atmosphere. Many satellite communications will be burnt out. Some satellite instruments will be destroyed. Communication, internet disruption. Well, with your fiber optics, you may be okay on the fiber optics, but any communication that's still over wires will be disrupted. We'll lose GPS, and that's something we depend on for many things now. We probably will have major power outages for weeks or maybe even more, and you can imagine what that's going to do to society and to the economy if there's no power available for a matter of months. If astronauts are out beyond low Earth orbit, they're dead immediately. Between Apollo 16 and Apollo 17, there was an X-class flare that did hit the Earth. And if the astronauts had been out beyond the Van Allen belts at that time on their way to the moon, they would have been killed instantly. And we could have given them no warning. That comes off the sun. Those particles come off at nearly the speed of light. But when we see it, the particles are following right behind. There's just no warning. The astronauts took a chance going to the moon. When astronauts go to the moon again, they will be taking that same chance. And it's not a safe thing to do. Those people are braver than the public ever gets told. Estimates right now is that a Carrington event today will probably result in about $2 trillion worth of losses to the economy. And so here's just a graphic of the kinds of things that happen when the Earth's magnetic field captures these blasts from the sun and captures cosmic rays. We get damage to the power systems on satellites. We can actually have the computers and the instruments on the satellites destroyed. Some satellites experience extra atmospheric drag and they re-enter the atmosphere. They're destroyed. Currents are generated not just in the power system and the electricity grid, but anything that conducts, for example, oil pipelines. And having very strong electrical currents running in oil pipelines is not a good idea. It'll disrupt radio communication, major impact to a lot of our society, and it's also dangerous for airline passengers when we get events of that order. If you'd like to follow up on that, or if you'd like to just see what's happening, if you'd like to see particularly, are we going to have any aurorae if you're going to go somewhere where you might see them, the Space Weather Prediction Center of the U.S. National Oceanographic and Atmospheric Administration is a great place to look for that. It'll show you these pictures of the sun and the UV. It'll show you the LASCO movies, and here are the auroral predictions. You can bring those up, and those will run as movies, and you can watch that auroral oval move around and see if the place you're going to be in's got a good chance for an aurora. So there are a lot of details. If I look at the bottom right here, this planetary K index, if that's over 4, there's an extremely good chance of seeing aurorae, and you'll see right now it's up around 5 or 6. If we were off in the auroral oval in the dark right now, we probably would be seeing aurorae. Now, if I take you farther away, the Earth's not the only planet with aurorae. There's a beautiful picture of Saturn, and there you can see the polar aurora on Saturn. Here's Jupiter, and there's the aurora on Jupiter. And we now know that there are flares and blasts off of other stars, and some of them are planet killers. Here's an artist's impression of a flare coming off the surface that we actually observed off the surface of a very cool small star, much smaller than the sun and cool, which has a planet orbiting it. And that flare blasted that planet. And what the artist is showing here is when it hits that planet with that strength, it blows away the atmosphere. That's a planet killer. This planet has no chance for life. These flares on its star blow away the atmosphere. One of the reasons we're here on the Earth is that our sun is a rather calm, gentle, mild-mannered star of its type, and it doesn't put out flares so big that they've blasted away our atmosphere, leaving the last 4.5 billion years for life to evolve here and for us to be here on the Earth. And so thanks for your attention. Thank you again for those of you who stayed through our little problems there at the beginning. And let's shift this to question time.
Thank you very much, Don, for your talk. We'll move to questions as we are a bit late, but still we'll try to answer as many as possible. Right, so there is a question from Roger, who tells that if solar mass eruptions have so enormous mass, even with sun being so huge, how can it still have any mass left?
Good question, Roger. The sun ejects approximately about 10 to the minus 10 to 10 to the minus 11 of its total mass every year. Now, let me see. The sun's total mass is 2 times 10 to the 30th kilograms. And so it puts out something like 2 times 10 to the 20th kilograms of material per year. That is that's 100 million tons. But it is so little that it will simply decrease the sun's mass slightly by the time the sun finally burns out in another 5 billion years. Much more massive stars, much hotter than the sun, have stronger solar winds, and they blow off material at the rate of about 10 to the minus 5 solar masses per year. In 100,000 years, they'll blow off an entire solar mass. But those stars typically have got 20 or 30 or 40 times the mass of the sun. And so that's not a killer for them either.
Thank you, Don. There is a question from Marisa Miseli. Does the sun have any effect on asteroids? does radiation or heat from the sun interferes with asteroid speed, trajectory, or lifespan?
The answer is yes. The sun has the wind from the sun and the radiation from the sun affects asteroids, and of course it affects them more if they come closer to the sun. Now, a comet is a kind of asteroid which just happens to have a lot of volatiles like water. And so when a comet, an asteroid with lots of water from the outer solar system, comes close to the sun, as you saw in that Lasco movie, the sun evaporates that material, and then the radiation and the wind from the sun blows it away. And so Halley's Comet, for example, the most famous of all comets, has been seen for about 2,000 years, but it's not going to be seen for another 10,000. Every time it passes by the sun blows away more material, and it eventually will evaporate and be completely disrupted. Now, when that happens, that material still orbits the sun, and there are old comets that are gone now, but the Earth runs into their orbit. And when that happens, all that material left over, those particles of dust and rock, smash into the Earth's atmosphere, and we get a meteor shower. And we have meteor showers quite a few times per year, and that comes from the sun disrupting things like asteroids and comets when they come too close to the sun.
Thank you very much, Don. Now question from Jenny Keeling, who is asking, do scientists have ways of predicting when solar flares would happen?
Oh, what a wonderful question. Boy, we're sure trying. When we see those big sunspots, we know there's a chance that there will be a big blast. And so that picture I showed you of the sun today, there's some small sunspots, but when a big one comes around the limb, it's not yet aimed at us. It'll be aimed at us when it gets in the middle of the sun. And so the space weather people at the institutes that follow this will put out advisories that there's a major active region on the sun, and there's a potential for a blast from the sun a few days later, seeing that coming. And we've got satellites that orbit the sun, and we can see the other side too. So we monitor those active regions very carefully. And the space weather prediction centers of the US, of Europe, of other nations put out warnings to industry, to science, to people who will be affected by these things, that there's the potential of one of these coming. And if any blast is seen, then the warnings go out immediately. Air traffic control, power systems. Since that event in 1989 did so much damage in Quebec, power operators around the world have hardened. They have made their power systems more resistant to the surge so they won't be blasted offline by an event like the 1989 event. It's possible they may still succumb to a Carrington event, which we still think is a once in 500-year event, but the next one will come.
Thank you. It's a bit scary, but nonetheless, there is a question from Jim K. Have any theoretical explanations been suggested as to why the sun has solar cycle of 11 or 22 years?
Yes, Jim. There is theory for that. It's not absolutely secure. There are problems still to work on, but it looks like it has to do with that convection zone in the sun, which is in the outer 30%, those rising columns, dragging those magnetic loops of the sun, those ropes, underneath the surface and circulating them from the bottom of the convection zone back up to the top and back down again. And it looks like in the sun that happens on roughly an 11-year cycle. But because we can see the effects of solar-like cycles on other stars, we know that those cycles can be very different length. And so we do not have a complete understanding of that, but it's not a complete mystery either. It is coupled to that convection and those magnetic ropes inside the outer part of the sun being circulated in the outer part of the sun.
Thank you, Don. And there is a question, perhaps somewhat related, from John Levenhall. Does the sun core has discrete regions, or it is a continuous gradient of gas pressure?
John, the sun has a continuous gradient of gas pressure, but we do mentally divide it into regions. So right from the surface, the core of the sun to the surface, everything has to be in what we call hydrostatic equilibrium. The gravity pulling in and the pressure pushing out have to balance with each other so the sun stays stable and it settles into that equilibrium state. But we would describe the sun as having a core, and what we describe as the core is the part where it's hot enough to generate energy by hydrogen fusion. And then as soon as you move farther out where the hydrogen fusion can't occur anymore, we then say that's outside the core. And the temperature gradient changes dramatically there. It has a significant effect on the structure of the sun.
Thank you. Now question from Lee. Why is the aurora on Earth green when on Neptune and Jupiter it's blue?
Well, it's green on the Earth, Lee, because largely the electrons are exciting. By exciting, I mean they're bumping electrons and molecular oxygen to higher energy levels. And when they fall, the energy difference between their levels produces green light. I'm not sure that the aurorae on Jupiter, I showed you Jupiter and Saturn. You said Neptune. Do we see aurorae on Neptune? Maybe, I'm not sure about that. You shouldn't go by the colors in the pictures, but the atmospheres of those planets are primarily hydrogen and helium. And I'm going to have to think about your question, Lee, and think about why that should excite those atoms to produce possibly a different color light. But the answer is going to be different atoms are excited. Earth, oxygen, and the other planets, primarily hydrogen and helium with a little bit of other stuff.
Thank you. There is a somewhat connected question to one of previous, so it's coming from Timur. I've heard that sun can have pulses of high solar activity. Why do they happen?
Well, Timur, the sun has high solar activity in the middle of its 11-year cycle. But if you can remember back, I showed a diagram going back to 1750, and the height of that cycle, how intense it is, varies from cycle to cycle. And so you'd like to know why, for example, in 1957, the intensity of the activity on the sun was incredibly larger than it is now. And I would like to know that too, and so would everybody else. And so I encourage you, Timur, to become a solar physicist and help us answer that question.
Thank you. Now a question from Alice. If the sun only goes as far north as the Tropic of Cancer, why does it get dark at 10 p.m. At the solstice, but further north in Norway it doesn't set?
Alice, the sun, right now it's coming up over the Tropic of Cancer, which means it's about 23 degrees north of the equator, shining down on the Earth. And that means everything within 23 degrees of the North Pole will not see the sun set. It's tipped that sunlight darkness line 23 degrees over with respect to the equator, and that entire polar cap within 23 degrees of the pole, the sun doesn't set. But then as you go to farther and farther south, the sun will set for a short time. And so if you happen to be in England now, then you're getting a few hours of darkness at night. But as you go closer and closer to the equator, the days get longer. And if you get to the equator, they're 12 hours long. It doesn't matter whether it's this time of the year or any other time of the year. You go to an equatorial country, Ecuador, Kenya, someplace like that, sun rises at 6 in the morning, it sets at 6 in the evening every day of the year. It never changes on the equator.
Thank you, Don. Now question from Anthony Bloxham. Thanks, Don. Is there a way to capture and use the energy produced by an X-flare to feed our energy demands?
Oh, wow, Anthony. I can't, for the likes of me at the moment, think of a way to do that. And also, I don't feel a strong need to do so because we have got an incredible amount, much more energy coming from the sun in the form of light. And we do know ways to capture that. And we're doing more and more and more of it. So although it sounds like the energy in those flares is incredible, it's tiny compared to the amount of energy coming in light that's hitting the Earth every day. And so solar energy, we'll go for that. We don't need to capture those flares, but I can't think of a way to do it if we wanted to. We'd probably destroy anything we put up there to try to capture it.
Thank you. Another question from Alice, who is fascinated by 11-year cycles. What will happen to that 11-year cycle as the sun comes to the end of its life?
Oh, very good question, Alice. I don't know. I don't think anybody knows the answer to that. We don't see cycles like that in red giant stars, which are not quite at the end of their lives, but they're well beyond the lifetime of the sun. And so that cycle, it's coupled to that outer convection zone in the sun. But as the sun grows larger and then cools, that convection zone actually gets deeper, but it's less dense, the circulation changes. And we don't at present see those solar-like cycles in the big red giant stars. And so the cycles like the 11-year cycle will almost certainly change in length of time, but it looks like they stop happening before the sun actually comes to the end of its life. And I can't tell you why.
Thank you. Another interesting question from Matthew Arnold. Isn't it amazing to think that the photons emitted in the core of the sun take 1 million years to reach the surface of approximately 600,000 kilometers, but only 8 minutes to reach Earth upon departing its surface?
It is amazing, Matthew, and the light's traveling at the speed of light the whole time, but once it reaches the surface, it can come straight here. Whereas as it's trying to work its way out, it is being a lot of it's from scattering. There's absorption processes too, but if we just talk about scattering, it's bouncing off of particles and it doesn't keep heading towards the surface. It goes sideways, it goes back down again. And it does what's called a random walk. And it's a nice little calculation for third-year students as undergraduates to calculate the distance light will travel between scatterings and how long it takes to get out. And you get an answer on the orders of 500,000 to 1 million years. And so, yes, it is amazing. And another amazing thing to think is that the light we see coming from the surface of the sun tells us what was happening in the core of the sun 1 million years ago. Now, we had a major problem understanding the sun over decades because we were getting too few neutrinos from the sun. They're subatomic particles. And one possible answer was that the sun wasn't producing so much energy down in its core anymore, and it'd be 1 million years before you find out. And we have been able to demonstrate that's not correct. We can demonstrate it through a technique called helioseismology, where we can see to the core of the sun. But we've done even better than that. We've detected the neutrinos, and we now understand what was happening. And so, but during the time of that problem, when we didn't understand it, we were somewhat stymied by the fact that the light coming off the surface was the light the sun produced in its core 1 million years ago.
Thank you, Don. Another question from Anthony Bloxham. I've heard reports that aurora makes sound that is sometimes audible at ground level. Is that true?
Anthony, I've heard those same reports. I've never heard it myself. I wouldn't dismiss that. That's high energy activity in the atmosphere. Particles are being excited and reconnecting. And you certainly know that if you put a lot of charge through the atmosphere and excite the atoms to where they're ionized, the pressure goes up and it expands. And then when the charging stops, it collapses again. The charger for that's called lightning, and the collapse is called thunder. So I don't know if that happens, but I wouldn't rule it out without trying to go look to see what's been written about it. I personally have never heard that.
Sounds very plausible, but yeah, indeed a good question. There are two connected questions, one from Nigel Satterley. We now have a lot of wind farms now around UK. The damage that Quebec suffered, I assume, could well burn out of the wind farms we have in Europe. And the second related question from John Eldon, but the flares will damage our solar panels, right?
Oh, that's a good question. I've got solar panels too. The flares aren't like an extra burst of light from the sun, so I don't think they're going to damage the silicon generators in your solar panels. that are creating the current. The danger is that the currents in the Earth's Van Allen radiation belts can induce currents in the wires that connect your solar panels to the rest of your house. And I don't know if that's a major problem on a small scale like the house. On a large scale like the big high tension power lines that go cross country, those things get big currents flowing in them. They're big conductors. I don't know what happens with small conductors like just the wiring in your house and whether it'll knock the wiring out in the house. That's a good question. I presume that's been looked at, but I don't know the answer. But I don't think it'll actually damage the solar panels themselves. It'll simply, they are conductors too, though. That's a good question.
And about wind turbines, wind farms?
The same problem. The major problem there is, will it generate currents in the cables that are carrying that power? And you know, the major problem in Quebec, it didn't actually burn out the wires. It blew out the power stations where you've got your transformers and you've got very high energy density. That's where the problem was. The power stations went down, or not the power stations, but the substations. And I don't think it actually damaged the wires. The wires were able to carry the current, but the current was so strong that the substations couldn't handle the current coming in. The transformers couldn't handle it.
Thank you. There is a question from Samuel Friedrich. Considering the maximum of solar activity in the middle of the cycle, does it mean that potentially damaging flares are to be expected in the middle of the cycle?
Yes, that's where they're most likely. And that's coming up in about 2026, but we've got a fairly small cycle this time.
And then actually one more question from Samuel Friedrich. I wonder if there is something like Earth shields being developed to protect us in the future.
Well, that's a good question. And I have to tell you that Earth shield number 1 is in place. It's called the Van Allen radiation belts. It's called the Earth's magnetic field. The Earth's magnetic field captures most of that high energy particles coming from the sun and then produces the radiation belts. Now, the effect of the radiation belts generating currents is doing the damage, but if the Earth did not have a magnetic field, those particles would penetrate right down to the surface and kill us outright. This would be a deadly planet without Earth shield number 1, the magnetic field. So, and sorry, but your question was, are we trying to think of a better way to do that? No, we're not trying to shield the Earth, but what's happening is the transformers in the power stations are being made stronger to withstand larger surges of power coming in when it happens again. So they won't stop the power from coming in from the currents that are induced in the power lines, but it will no longer blow the transformers off. It will shut the station down. But as soon as the event's over, they'll be able to turn it back on again and get your power back up. And so it won't be weeks that the power's down. It'll be briefer than that, maybe much briefer.
Thank you. There is a question which also connects with some of our previous Astro-Chats, I think, from Phil Riggs, who asking, is the hydrogen to helium reaction the driving force of all stars, or there are stars which emit energy through a different reaction?
The answer is yes to both of your questions. All stars at the beginning of their lives fuse hydrogen to helium, and that's what they do for 90% of their lives, because 90% of the energy available from fusion is from fusing hydrogen to helium. But when stars become old, and you've actually just indicated I should do a future Astro-Chat on the evolution of stars. That's a good topic, Andrei. We'll do that one. When the sun gets old, when stars get old, and the hydrogen in their core is exhausted, the core squeezes under gravity and it heats enough that it can then begin fusing helium to carbon. And so the red giants, the red supergiants, which are near the ends of their lives, for about 10% of the life of the star, it can be powered by fusing helium to carbon. And then for very massive stars, not the sun, but for very massive stars, they can go beyond that and fuse carbon and helium to oxygen, and they can make heavier and heavier elements until they have built up a core of iron. And then you can't get energy out of iron by fusing it. That's a dead end. Other things can happen, but not fusion energy. So all stars spend 90% of their lives fusing hydrogen to helium, another 10% fusing helium to carbon for all but the very tiniest stars. And then the massive stars can spend a little bit of time fusing heavier elements. Hydrogen to helium is the main one. That's what powers the visible things in the universe.
Thank you, Don. There is a question from Steve Dever. Is the period of star cycle related to its mass?
I don't know the answer to that, Steve. That work has been being carried on now for about 40 years in terms of just observing the stars, and I haven't looked recently. I was interested when I was young. I haven't looked recently to see what the correlations are in the links of those cycles with other parameters in the stars. I suspect somebody does know the answer to that, and that information's available, but it's not in my head.
Thank you. I see that we are approaching our time, even though we kind of extended it. So just scroll if I miss some burning question. Just a second. Oh, there was a question. I forgot who that was asking. Basically, if solar flares would also be dangerous for our nuclear plants.
To the extent that those nuclear plants are generating electricity and the electricity is being carried on high power lines, and I would imagine that in the nuclear plants, you've got transformers and things like you've got in other power stations. They need to be protected too. I'm reasonably certain that everywhere around the world, they will have been the first power plants that have been beefed up and given extra protection against surges that could cause those sorts of problems. I'm not particularly worried about that. I'm confident that in all countries, people with nuclear power plants will have protected them against the kind of surge that we saw in 1989 and the kind of one that we expect with another Carrington event.
Right, and I think we're almost there, but there is still one question, which will be final one from Graham Burrell. How often can you see the Aurora Australis in South Africa?
Oh, Graham, almost never. I have lived in South Africa in 2 different times for 27 years, and we've had one occasion at that 1989 event where the aurora was visible off to the south that I know of. Now, let me think about that. I think I might have heard some reports from some other people, but I have to tell you what it means to see the aurora. The aurora will be very far to the south where that oval is. And so it's not like the pictures I showed you where it's overhead. You would see it looking out to the southern horizon and you would just see kind of a glow on the horizon. And some of you in the UK may have experienced that. Occasionally you get reports of you can see the aurora now in southern Scotland or even in the north of England. But the people who are reporting that are not seeing these beautiful sheets of green and red rippling light overhead. They're seeing a glow off to the northern horizon. It's not the spectacle you get if you're standing right under it. And so very, very seldom in South Africa, and only as a glow to the south, which you can identify as an aurora. But if you've never seen one before, that's not going to excite you if that's your first one.
Thank you, Don, very much. The wonderful talk, answering question. Thank you, everyone who stayed with us in spite of technical difficulties in the beginning. We really appreciate that. We also will send you email asking for feedback as usual. And I just also tell that we now also posted on our YouTube channel video recording of Don's face-to-face public lecture he gave here in Lincoln in the spring, and we posted it now with improved sound. So if you wish, so you can also watch that one and comment, and we will read all your comments and answer if you can. Thank you very much, everyone. Thank you very much, Don, and we see each other in one of our future Astro-Chats. Bye.
Bye, everyone.